Neden? Onu bilmiyorsunuz da öyle
Neden oluyor? Şaka mı?
So last time we started talking about making a single threaded code multi-threaded. That was our last topic. We said that if you have a procedure that uses only the local variables and parameters, it is okay because since each thread has its own stack, and all the local variables and function parameters are stored in the stack, and that means that each thread should have its own copy of local variables and the parameters. So there is no problem if our functions all use their local variables and the parameters. The problem is the globals. Since the globals are shared, if one thread reads a global and the other thread changes it, then it becomes a problem. So we should be careful about using globals when we are writing multi-threading applications. So maybe we should avoid using globals altogether. That's one solution. Don't use globals at all. But sometimes we need globals to communicate information between the threads. So this is not a good solution. Another solution is use globals as, if you are not going to use the globals as a communication mechanism, maybe we should use the globals as special kind of parameters. So the suggestion from the book says that create global buffers. Okay, create global buffers. That means that when you this is a buffer, global buffer. Its name is this one. Okay, this is a new library routine. Okay, this is creating for the globals, and this is for setting the global. This is for reading the global. So you are using specialized functions to read and write the globals, and you are sending these buffers. You are sending these buffers, okay, to the functions as parameters. So in a way that we are sending our globals as a parameter to the function. In that case, our globals would look like this. Okay, each thread has its own code. Okay, this is thread 1. This is thread 1 code. This is thread 1 stack, and this is thread 1 globals. So each thread has its own local variables, parameters, and the globals. That's one solution for the having globals. So we are discussing this. How can I write multi-threaded applications? Writing multi-threaded applications is different from writing multi-process applications, because when I write a single process application, as I said last time, I don't care if there are any other processes in my computer, because I am completely isolated from the rest of the computer by the operating system. So it is very easy for me to write a single application that contains only a single process. But if I am writing a multi-threaded application, since I am writing all of those threads myself, okay, I am using them all of them myself, and I am sharing my my memory space, I need to be careful. That's why these globals are very big problems for the multi-threaded applications. So many people suggest that, including the object-oriented people, they suggest that don't use any globals, don't use any statics, okay, because they are very bad for the sake of multi-threading. Okay, what else? We are calling lots of library routines like the printf or the scanf or memory allocation malloc or the API, that kind of standard library routines we are calling them, okay? But not all of them are good for multi-threading applications. Why? Why they are not very good for multi-threading applications? Because many of the standard C routines, standard C functions, they use static memories in them. Okay, they have static in them. So if one function, if one thread calls it, and at the same time another one calls it, okay, two of them are trying to use the same function at the same time. It will create a problem because the static local variables are shared, and if one thread changes that static, the other one will get affected, and those standard C functions will not function very well. They will create lots of problems for the multi-threading application. So it says that library routines may be used for more than one thread simultaneously. Not all routines are prepared for this, especially standard C routines are not prepared for this, because when they were designed, they didn't care much about multi-threading. I mean, they had multitasking. In the multitasking, all the tasks are isolated from each other. They are using different memory spaces. So for the multitasking, time sharing, it is okay to call the same function from two different processes because they are isolated. But when they invented this multi-threading, execution of more than one procedure at the same time on a single process, then we start having these problems. Not all C routines are prepared for this kind of multi-threading applications. So static variables can be overridden by another thread, and all of the functions that we call must be reentrant. What is reentrant? Reentrant means it can be invoked more than once simultaneously. Okay. At the same time, if I have a function and I can call that function at the same time from two different threads in the name memory space, then it's a multi-reentrant routine. Okay, reentrant routine. This one, for example, very simple one. I think I wrote this one last time. I'm going to write it again. It returns an integer. And it takes another, let's say, integer a. It just returns a plus just one. I think I wrote exactly the same thing. So this is a reentrant. This is a reentrant function because it doesn't use any static variables. It doesn't use any globals. So it doesn't have any memory actually. So when I call this function f, I provide my parameter in the stack of my thread. Since the stacks are isolated between the threads, it's okay. This function runs and it returns to the address that it was called. So it is no problem. But if I, as I said last time, if I add this static integer b and kind of do this, okay, and I return this one. So maybe this is not a every time. No, let me do this. Let me static. Okay, it is b. The first value is 1, and every time I am calling this, I am making this. Okay. So every time I increment the number b by 1, every time I call this function f, I increment the number b by 1. So if you call this many times from two different threads, from each call, you will get this number being incremented by 1. So the other thread will think that I didn't call this one, how come this is increasing every time? It doesn't know that how many times the other threads are calling this. So this is not a good reentrant function. This is a bad reentrant function. Why? Because it is using this static variable in it. Or if I had used global variable in it, again it wouldn't be a good reentrant routine. Okay, so for the reentrant routines, you say that you can use only local variables or dynamically allocated variables. You allocate your variable yourself and use it again in your function, or it should be local variable or the parameter. Okay. It should not use static variables. It should not use global variables. You can read global variables, but you should not write to global variables because that has side effects. Okay, and many C library functions actually do not use the static buffers, unfortunately. So standard C functions are not very good for this kind of work. We should be careful. We should be very careful about the usage of them. You should carefully read their documentation to see if they are re-entrant or not. For example, the standard C function malloc, memory allocation. Okay, this function, it takes some size t, right? Size t. This one is not re-entrant by default if you are not using the special version of it, because it uses some linked list structure to keep track of the memory. Okay, it has some linked list in it. Say that, for example, inside the linked list, okay, say that, okay, this part I have a memory 2K, in this part I have memory 4Ks, in this part I have memory 4Ks, and it assigns these memories to the threads or the processes whoever calls them. So if I call malloc at the same time 2 times from 2 different threads, the maintenance of the linked list will be messed up. So malloc will not work very well. So the standard malloc is not a re-entrant routine. Standard str talk, again, str tokenize, str talk, again it uses static variables in it. It's not a re-entrant routine. Okay, so the book has another example. The book says that local time. Local time is a standard C function. It takes time information, okay? It takes time information. It has some static memory in it. It fills that static memory with the time information and it returns a pointer to that static memory. Okay? It returns a pointer to the static memory inside the function local time. This is not a re-entrant function because it uses static memory. So if I wanted to write the same function as a re-entrant way, I should do this. Send the time information, also send the buffer, okay, send the buffer to be filled in. You send your all of your memory you send all of your memory with the parameters, function parameters, okay? So you fill in the sent memory and you return a pointer to this memory position actually. So you don't return anything to the static variable. So this is the re-entrant version of the local time. Normal version stores the result in a static buffer, which is that. Okay. So I am not going to go into details of the writing multi-threaded application, etc. That's the task of the systems programming course that we had last year. But these are just points. I mean, when I discuss about this, it makes understanding the thread versus processes easier or more clear. Okay. Any questions about re-entrant routines or the writing multi-threaded applications? You have written multi-threaded applications, right, in systems programming. You have written multi-process applications too. Yes. Okay, so you already. Okay. So already you should know the details. Most of the computer engineering departments they don't offer any systems programming course. So most people don't know how to write multi-threading application or multi-process application. So you are lucky in, I mean, I think you are lucky. You may think the other way, but you have this opportunity. So what I said was at the beginning of this class, I said that global variables are problems. But, okay. globals to the entire program are problems because one thread might change it, the other one might be reading it, so there might be some problems. But sometimes we need this. Sometimes we need globals. Sometimes we need globals to communicate between the threads. Okay. Sometimes there are global variables that you have to use. I have to use it because between two threads, I need to send some information. Let's say I calculated a number and I need to send that number to another thread. And using a global is a very good way of doing it. So we should not abandon using globals altogether. Sometimes we need it. The whole purpose of the thread is actually, why are we using the threads instead of the processes? Because they are using the same memory space. Since they are using the same memory space, that's an advantage. Let's take advantage of that feature of the threads. In that case, I can use the globals for my advantage if I am careful. Okay. So when you are using globals, globals are no problems for the processor, right? That's no problem. Globals are need to be used very carefully with the threads, and there are some synchronization issues, and there are some other issues too. If we are careful about the synchronization issues, then we can use our globals to our advantage. Okay, so that's the topic of inter-process communication. Okay, if I wanted to communicate between two threads, or if I want to communicate between two processes, then it's called inter-process communication. And there are many ways of doing it. There are many ways of doing inter-process communication, and you have seen some of them in the systems programming course. You actually coded some of those stuff too. There are some issues with the inter-process communication. What are those? The first one is how one can pass information from one process to another process. That's one thing. Standard POSIX interface defines lots of stuff. One of them is the shared memories. The other one is pipes and that kind of stuff. And other than the standard POSIX interface, there are other things like the remote procedure calls and etc. There are many techniques to do this inter-process communication. So that's one thing, but I'm not going to talk much about this issue because this is an operating system course. We will talk more about the problems that are created when you are doing the inter-process communication. By the way, this is very easy. This is very easy for the threads because you don't need to use any tools to communicate between two threads. You just use a globe, right? So you don't need any libraries to communicate between two threads. Okay. So there are three issues with inter-process communication. The second issue is if two processes, okay, if two or more processes, they wanted to access the same data at the same time. Okay. Let's say there's a good example from the book. Okay. Two processes in an airline reservation system, trying to grab the last seat on a plane for a different customer. So there is one single resource available from the memory, and two processes are trying to grab the same resource at the same time. This might be a problem. Actually, this might be a problem for the threads too. This is not a problem for the threads, but this is a problem for the threads and the process at the same time. The third issue is proper sequencing. If process A produces data and process B prints them, B has to wait until A is ready. One is producing, the other is consuming, okay? The consumer cannot run without producer producing anything, okay? And sometimes producer cannot continue producing until the consumer consumes it because I don't have enough space to put all those produced items, okay? So there is a sequencing order, okay? Sequencing. Proper sequencing. Okay, so one is how do you do the communication? Okay, we will not talk about it. Actually, it's very easy for the threads. The second one is processes do not get each other's way. Okay, don't try to grab the same thing at the same time. And the third one is proper sequencing. So we will look at these two problems in detail for the rest of this subsection of the book lecture. Any questions so far? Okay, let me continue then. So there is this term race condition. Okay, race condition, this is the definition. When two or more processes are reading or writing some shared data, and the final result depends on who runs precisely when, are called race conditions. If you have two processes or two threads, okay, you are trying to read and write on the shared data, and the final result depends on who runs first or who runs second. Okay, that's called race condition. This is not a very good way of programming multi-threaded application, because if I run my application, it produces this number 500, and if I run it again, now this time it produces 600. Every time I run my application, it produces a different number. That's not a good thing, because it means that my program is dependent on who is running first, who is running second, okay, and what kind of decisions the operating system is making. That's called a race condition. Race condition is not a good thing. It's a bad thing, and we should prevent it. Okay. So if two processes are trying to read and write on the same shared data, and the final result depends on who is running precisely when, then we have a race condition, which is bad. We don't want this. We always want our results to be the same. Doesn't matter when I run it. Doesn't matter on what computer I run it. Doesn't matter what time of the day I run it. Okay. It should not be different from time to time. And race conditions occur if I have more than one thread trying to read and write on the same data. Let's see an example. This is an example directly from the book. Okay, exactly the same example from the book. Let's say I have a spooler directory. Okay, processes, they want their files to be printed. If you have a file, you want it to be printed by the printer, you put your file name inside this slot. Okay, say that, okay, the in position is 7. So let's say process A wants to print this file, my file.c. Okay, the process A wants to print that file, so it puts this name, my file.c, into this slot. But in that case, it should increment this number to 8, so that another process comes here. Let's say process B. Now process B comes here and says that, okay, I want to print this file backup.cpp, and okay, it puts this file name inside this directory, and it says that, okay, now the in is 9. Okay, now it is pointing to 9. Both of them are pointing to 9. The printer spooler comes here. Okay, when the time is okay, it comes here. Okay, say that out. Who's first to be printed? ABC. It takes this ABC, it prints it, and it says that now out is 5. So your processes are adding files to the end of this spooler. Your printer daemon, it prints these files one by one, and it increments these numbers. Okay, so both of them are incrementing. One is from the beginning, one is from the end. So there are two global variables here. One is out, one is in. Also, the other global variable is this string array. Okay, I have a string array. Inside the string array, I put my file names, and I increment these numbers one by one. Since they are shared, process A or process B or the spooler daemon, it can read and write to these numbers. So let's see what kind of a race condition I have. Let me try to write the code, the process A and process B process A and process B process A and process B executes actually. It's kind of a code, something like this. Okay, I have a array. I have a string array. Let's say I have 10 of them, and this should be my files. Okay, this is a string array. Its name is files, and in is the empty position that I can write my position. So the process A runs this code. It says that, okay, I'm gonna put this myfile.c into this in position. So I will say, okay, this is n. Okay. There are n of them. Okay. Question? No, I don't. I will not write the whole thing. Actually, I will. This is my string array. Okay, and these are my just indexed global variables. I will say that files in is f.c. Okay, so let's say process A is trying to put f.c here. Okay, let me erase these, and then what I'm going to do and do what? What I'm going to do now? We should increment this in global variable, and that's it. Okay, this is the process. This is what process A is doing, right? So a similar thing is done by the process B. Process B will try to put files in some other file name, and it should increment the in pointer. The problem is this. Okay, this is process A. This is process A. Let's write the process B version. Process B will do the similar stuff. Files in, let me see, it is g.h, okay, and in ++. If I run these two codes separately, different from each other, there is no problem. Each one is writing their file to the array and incrementing the global variables, no problem. Both of them are okay. But the problem is this: when I am running this process A, okay, I executed this line. This line is executed. Okay, this line is executed, and my operating system decided to block my process A because I used too much time, and switch to process B. Remember what I did? I wrote this f.c into this position, but I did not increment n. Okay, it is still 7. So I am running this now. B. When I say files in gets this string, so what I am going to do now? I am going to erase this one, and I will say g.h here, and I will increment in by 1. In will be now 8. Okay. So after that, I will switch back to this process A, and process A will increment this in by 1. So it will be what?
9 olacak 8 yani.
It will be.
Bir tane boşluğa attırmış olacak.
It will be what? 9 or 7, 8.
9.
9 or 8. No, the answer is 8. Why? Actually, it depends, because I already, maybe I read my global variable into my register, okay? I read this global variable into my register, I use that register, and I am incrementing that register, and I am going to put it back to the global variable. So it could be again, since n is 7 in this case, When I increment it, it will be 8, and it would put this number 8 into this position again. So at the end, there will be a bad thing. What is the bad thing here? The bad thing is that I lost this file name. That file name will never be printed. Okay, that file name will never be printed. And the printer spooler doesn't know if there is a file missing. And the owner of the process A will wait for this file to be printed from the printer, but it will never receive it. So there is a race condition. What was the definition of race condition? There are two or more processes reading or writing some shared data, and the final result depends on who runs first or what kind of sequence they are running. Okay? If they are running in sequence, first A, then B, there is no problem. First B, then A, there is no problem. The result is the same, right? Both of the files will get printed, FC, F.C and G.H. Both of them will get printed. But in this case, when the operating system decides to switch while the process A is running, then the result will change. This is a very typical race condition. And this should not happen, okay? Your result should exactly be the same, what kind of order you use for the execution of your processes. Okay? Situations like this, where two or more processes are reading or writing data, and the final results depends on the order, are called race conditions. Okay? So, to prevent race conditions, there is this solution. To prevent this race condition, there is the solution of mutual exclusion. Mutual exclusion. What does it mean, mutual exclusion? Mutual exclusion is when you are reading or writing your shared data, okay, you should do it in a mutually exclusive way. That means that only one process can read or write data to that to that shared position. Okay. What we need is a mutual exclusion. That is some way of making sure that if one process is using a shared variable or file, the other processor will be excluded from doing the same thing. So only one process at the same time can access that shared data. So if I said that only A or B can access this global variable in at the same time, okay? So operating system cannot switch from process A to process B while I am reading and writing this global variable n, because it will be a mutually exclusive global variable. So if I have a mechanism like this, mutual exclusion, then I will not have problems like race condition problems, because I cannot switch between one process to the other process while I am modifying those global variables. Where did the problem happen? The problem is this. I read this into my register. Before writing it back, I switch to some other process. Okay? So this should not happen. You read your register, you read your global data into your register, you modify it, you put it back. Only after that you can switch to some other process. Okay? So this is called mutual exclusion, and we will try to achieve this mutual exclusion using several tools actually. I will show you at least 7-8 different methods of doing it, starting from the simplest one, and simplest one will have problems, and we will go more and more advanced ones, and we will see how the Unix standard interface, POSIX interface, supports this kind of tools to prevent race conditions. Okay, any questions?
Hocam, şurada B'de hani yine arttırdı 8 oldu ya hocam. Bir daha A'ya döndüğümde bir sonrakinde yine int'i 1 arttırmıyor mu?
Register'e yapmış.
Şimdi bunu C olarak düşündüğümüz için burada göremiyorsun ama şimdi int doğrudan memory arttırma diye bir şey yok, tamam mı?
Yok.
Çoğu
Yani-
CPU'larda yok. Register'ı okuman lazım değil mi? Şimdi ben bu yine register'ı okudum. Files'ın o register'da yazan kısmına bunu yazdım, tamam mı? Register'ı bir tane arttırıp geri hafızaya koymadan switch oldu. Geri geldiğinde register içerisinde in'in daha önceki değeri duruyor, 7 duruyor değil mi? Register'ı bir arttırdım, 8 yaptım. Ondan sonra tekrar memory'e koydum in pozisyonuna. Anladın mı? Yani C gibi düşünmeyin, SMD gibi düşünün. İşletim sistemlerinde çoğu zaman C yazıyoruz ama alt tarafta dönen numara assembly. Çünkü çalışan şey assembly. Tamam. Şeyimiz bu. Buradaki numara her zaman için bu. Hiçbir zaman yani buna geleceğiz. Eğer şu işlemlerin hepsini bir tek adımda yapabilseydim ben, şu ikisini beraber, arada switch olmadan tek adımda yapabilir. Nasıl yaparsınız onu? Switch olmasını nasıl engellersiniz şurada?
Atomik yapalım.
Çevresini artırsak.
Tabii yaparız. Güzel laf da nasıl yaparsın?
Hocam atom.
Beraber yaparız demek ki bir şey. Beraber yaparız.
Olabilir belki. Ancak
Atomik diye bir şey anlatmadım, sen de bilmiyorsun. Söyle ya, atomik diye bir şey bilmeden söyle bak. Nasıl yaparsınız?
Şu an files in artı artı desek, yani post increment şeklinde files in artı artı desek B noktacı.
Güzel, C'de bir tek adımmış gibi ama bunun SMB'sini çıkar karşına kaç adım çıkıyor? En az o 10 satırlık falan bir assembly rutini söyleseydin yani. Files'ın hem in artı tek satırda yapıyorum işte. Hem atama yapıyorsun, hem onu yapıyorsun, hem yok. En az 10 adımlık bir tane assembly rutini. Nasıl yaparsınız? Switching nasıl oluyordu? Şuraya geldiği zaman bu prosesten bu proje nasıl switch oluyor? Hayır, yıl yazıyor mu orada? Yazıyor mu yıl? Ben yapmadım switch falan. Demek ki işletim sistemi yapıyor switch. Şey değil, bunlar proses yapıyor.
çok çalıştı.
Nasıl oluyor?
Zaman kaybettiği için running'den bir şey oluyor.
Bir prosesten başka prosese nasıl geçiriyor dedi işletim sistemi bize? Ya kendin blok olacaksın değil mi?
Yani,
Bir proses nasıl durdurulur? Bir prosesin blok olmasının şeyleri ne?
Ya IO gelecek
yazıyor?
ya
Ya onu yazma ya da benim gözümün önünde yazma ya. Başka arkalara gitsene. Arkaya git.
slide yazıyor orada.
Ha?
Slide yazıyor.
Slaytı mı yazıyorsun?
Evet.
Dersini notlarım ya.
Evet.
Hiç beni dinlemiyorsun ama. Dinlemeden yazıyorsun. Ne söyleyin yollara bana. Bir proses nasıl blok oluyor?
Ya IO olacak ya da operating system running'den değil.
Burada yok falan olduğu yok. Ya da ne interrupt değil mi? Kim söyledi interrupt? Tamam. Burada interrupt geldiği zaman ne olacak? Timer interrupt'ı çat diye buraya geliyor değil mi? Yani timer interrupt'ı olduktan sonra ne yapacak? Adam diyecek ki başkası çalışsın birazcık da ya. Şimdi burada timer interrupt'ı gelmesini nasıl engellersin? Interrupt'ları disable edebilirsin değil mi? Interrupt'ları disable et başlangıçta. Diyorsun ki ben 2 tane satır çalıştıracağım. Bu interrupt'lar burada disable olsun. Çözümlerden bir tanesi mesela bu. Olabilir.
Ama direkt o saat etkilemiş olmuyor muyuz?
Onun hakkında konuşuyoruz, onun negatif tarafları falan vardı. Her zaman da çalışmıyor zaten. Ondan hakkında yani bu tür yöntemler kullanacağız. Beraber yapalım arkadaşlar, iyi atomik yapalım falan diye. Yöntemlere bakacağız ya da software on the solution'lar var. Sadece yazılımla yapabiliriz bunu. İnternet falan filan bırak. Mesela girmeden önce birisi bir yerden izin alsın falan gibi şeyler. Onların hakkında konuşacağız. Bunların hepsi race condition'ları önlemek için yöntemler. So, mutual exclusion is this. Some way of making sure that if one process is using a shared variable or file, the other process will be excluded from doing the same thing. Okay, so when I am doing this too, I will exclude any other process to do the same thing on this global variable. Mutual exclusion. Okay, and part of the program where shared memory is accessed is called critical region or critical section. So this will be my critical region. Critical region of process A and critical region of process B. Okay? Critical region of process A and critical region of process B. Inside that critical region, I have the mutual exclusion of using that global variable. Okay, I have the mutual exclusion of using that global variable. That's called the critical region. And you should say that, okay, this is my critical region, and inside this region, only I can access this global variable, so there will not be any other access to that global variable. Even though there might be a switch between process to process, no other process can enter the critical region without I leave that critical region first. Okay, so there are some rules for the critical regions. If you write your critical regions using these 4 rules, there will not be any race conditions. What is the definition of race condition again? I repeat it maybe 3 times. For the 4th time, race condition is if you are running more than one thread and your final result depends on who is running first or the sequence. This should not happen, okay? Your final result should not depend on the sequence of your processes. Okay. So in order to prevent these kind of conditions, rate conditions, you should have critical regions, and these are the rules for critical regions. No two processes can be simultaneously inside their critical region. So process A and process B, they cannot be at the critical region at the same time. One of them is in the critical region, the other one cannot be in the critical region, because if you are in the critical region, you are modifying that, you are accessing that global variable, okay? So the most important requirement, no two processes can be in the critical region at the same time. Second one, no assumptions can be made about the speeds or the number of CPUs. You cannot say, okay, you cannot say this. Process A is in its critical region. In a few milliseconds, it will be out, so I can go in. No, you cannot say that, okay? Process A can stay in the critical region as long as it wants, okay? As long as it wants, okay? Or you cannot make any assumptions about the CPUs. You cannot say that no two processes can be in the critical region at the same time because I have only one process. Okay, you cannot make these kind of assumptions. Or you cannot say that process A is running much faster than process B. Before process B starts, process A will be done by the critical region. No, these assumptions are not valid if you want to avoid race conditions. Okay. 3. No process running outside this critical region may block the other process. If nobody is in the critical region, then you should be able to go into the critical region. The only way you can be blocked from entering the critical region is that somebody else is in the critical region. If there is nobody is in the critical region, then it should be free for you to go into the critical region. This is the number 3. Okay, and the number 4, no process should have to wait forever to enter its critical region. I mean, I can wait for a long time to enter the critical region, but it should not be forever. Okay, otherwise it will be an infinite loop, and it will render my application useless because one of my threads are waiting for them to enter the critical region forever. So these are the 4 equally important requirements, but the first one is the fundamental requirement of no two processes can be simultaneously inside their critical. This is mutual exclusion actually. This is mutual exclusion. Okay, so let's see some examples. This is a very good diagram from the book again. Process A and process B. Process A enters the critical region at time t1, okay, and process while it is working on it, process B wanted to enter the critical region t2, but it cannot. It will be blocked until process A leaves the critical region. Then process B enters the critical region and it leaves it. So the process A takes longer time to the critical region. This takes shorter time. This is okay. The thing is that they cannot be at the same time in the same critical region. They should take turns to go into the critical region and out. They cannot wait inside the critical region forever. Okay, you cannot block somebody else from entering the critical regions forever. And as soon as process A wanted to enter the critical, it entered because nobody else is using it. Okay, let's look at some examples of how we deal with these critical regions and mutual exclusion. Okay, one technique is busy waiting. If process B cannot enter the critical region, it goes into a busy wait loop. What is a busy wait loop? It's an infinite loop. It's not an infinite loop. It's a idle loop that keeps looping until the critical region is available to enter. Okay, it's called busy waiting, and these are some examples of busy waiting: lock variables, strict alternation, Peterson's solution, and the TSL instruction. And we will see them one by one. So busy waiting is very easy to implement. It's a software-only solution, and some of them works very well for some cases. But there is one serious issue, very severe issue with the busy waiting, and we will see what that is. Okay. So before going to the busy waiting solution, let's talk about the disabling interrupts problem again. What did we say before when I wrote this? If I wanted to disable interrupts between these two lines, there will not be any process switch, right? I cannot switch from one process to another process if there is no clock interrupt. Since I am not clocking myself, doing some kind of a system call, then these two lines should execute one after the other. Okay. So what is the problem with the disabling interrupts then? I said that is not a good solution. The first one is somebody says something. You cannot disable the interrupts as a user. Disabling interrupts is a privileged instruction. Okay. Not everybody can disable the interrupts. If I can disable the interrupts of the whole CPU, whole system, then if I wanted to do bad things, then I can do it, right? So ordinary users, ordinary processes should not be allowed to disable the interrupts. Okay. That's one thing. What other things are you? Do you have another? That's one thing. Okay. Let's say your system is a very small system, and it is yours, and your system trusts you, and you want to disable it. What other problems do you see?
Başka interruptlar gelirse onları da kaybetmiş olacağız.
No. Well, if you operating system always disables the interrupts time to time. It is okay to disable the interrupt for a few microseconds. For two lines, if you disable the interrupt, the incoming interrupts can wait. That's okay. What other things do you see? Let's say if you have more than one CPU, right? If you have more than one CPU, process A is running on CPU 1, process B is running on CPU 2, right? You don't need any interrupts to switch from A to B because they are running literally they are running at the same time because they have more than one CPU, right? That's the other thing. So disabling interrupts is not a feasible solution in terms of operating system security, and it is not a feasible solution if you have more than one CPU. And more than one CPU or more than one core is not an exception anymore because even the simplest computers nowadays have many cores. Some of them have actually 16 cores, etc. So this is a serious problem. So disabling interrupts is not a very good solution. Available to the kernel, better not be available to the user processes. Doesn't work well on multiprocessors. Okay, and maybe it could be a special case solution for the kernel only. If you are doing this race condition solution in the kernel, maybe in the kernel for a single CPU, maybe you can do it. But as a general solution for preventing race conditions, this is not a good solution. Okay, any questions? Bir soru sorunlara verin.
Hocam her prosesin kendi mi timer'ı var? Yani her proses kendi için timer.
Proses scheduling bu chapter'ın sonunda gelecek.
Şey olarak, işlemci olarak demek istedim. Yani birden fazla çekirdek var dedik ya.
Evet.
Bunda da şey yapamıyorduk. Disable edemiyorduk interruptları. Yani
edersin de gitmenin bir manası yok çünkü proses A birinci CPU'da çalışıyor, proses B ikinci CPU'da çalışıyor. Aynı anda çalışıyorlar zaten. Tamam mı? İkisinin interrupt'ını disable et, zaten çalışıyorlar. İkisi de critical region'in içerisinde olabilir. Bu orada tek CPU'da vardı. Şimdi adamın bir tanesi critical region'ın tam ortasında interrupt switch oluyor, öbürüne geçiyor değil mi? Bunu engellersek tek CPU'lu durum için, o zaman race condition olmaz diyor. Ama birden fazla CPU olduğu zaman bu çalışmıyor. İkisi aynı anda çalışabiliyor çünkü. Tamam, mesela sen 10 dakika verelim.